Hi, I am Dr. Abhishek Joshi, and in this video lecture I am going to discuss about how we can launch the optical power from the source to the fiber. So we know that we are having optical source such as LED or laser. In my previous lectures we have discussed how the LED and the laser work. So in this lecture we will see the optical power generated by these optical sources will be launched to the fiber. So fiber, we have studied that either we have the single mode fiber or the multi-mode fiber, or we may have step index fiber or the graded index fiber. So this is the content of this lecture, that is the optical source to fiber coupling and the power launching. Then the coupling or the launching technique. So there are different techniques through which we can launch the power to the fiber. We will study about the examples of the lens based coupling or the launching techniques. Then the parameters deciding the power launching or the coupling, and the source output power pattern with its example. So let's start. So what is the coupling efficiency? So the photons or the light which is generated by the optical source, it may be LED or the laser, whatever source we are using, LED or laser, it generates the light. Now light is generated, but all the light which is generated by the source will not enter the fiber, because we know that the fiber itself have the acceptance cone. If light doesn't fall within the acceptance cone, it will lost in form of radiation. It will never enter the fiber. So there is a coupling efficiency. So whatever power is generated from the source is given by P of S, and the power which is entering the fiber is P of F, that is power entering. So we can find the coupling efficiency, that is eta, that is given by the power coupled into the fiber, whatever power entering in the fiber, that is P of F, and the power generated, that is the optical power generated by the source, that is LED or laser, is P of S. Then power coupled into the fiber, that is P of F, divided by the power emitted from the source, that is P of S. So if we consider an injection laser, then how we can couple the power from the injection laser to the fiber? So let's discuss this. So one of the major difficulties with using the semiconductor laser within the optical fiber communication system concerns the problem associated with the efficient coupling of light between the laser and the optical fiber. So they have the diverging output fields which do not correspond to the narrow acceptance angles of a single mode fiber. So butt coupling is simply when we are placing the optical source near the fiber, it is known as the butt coupling. So butt coupling efficiency from the laser to the fiber is often low at around 10%, even with a good alignment and the use of the fiber with a well clipped end. So if you are directly placing any source near the fiber having the core and the cladding, this type of arrangement is known as the butt arrangement. But this butt arrangement, as we have seen, that it is having the efficiency of only 10%. This means it's an inefficient technique. So let's see, there may be different techniques. So first technique is the butt technique or the butt coupling, where we can see the laser is acting as a source and it is emitting the light, and directly we are placing this laser near the fiber. Whatever light enters the fiber, it is propagating inside the fiber. Next one is a tapered hemispherical fiber coupling. So here we have the tapered hemisphere and the light which is generated from the laser enters the fiber core, and it is more efficient than the butt coupling, because here we have the tapering in the cladding, and here we have the core. Now the another technique is using the lens. As we know the property of the lens, that if you are using a convex lens, it converts to the light to the focal point. So the focal point, we are keeping it as a face of the core. So here we have the laser which is generating the light, and the confocal lens system, where we are using two lenses, two convex lenses, and we are focusing the light to the core of the fiber. So here we have the core, the center part is the core and the outer part is the cladding. The focal point of the first lens, that is convex lens, is f1, and for the second lens the focal point is f2. So light is focused at the core of the fiber, and the addition of these focal point is the distance between the two lenses. So this is the techniques for coupling the injection laser to the optical fiber, and we have discussed three techniques, that is a butt, then the tapered hemispherical, and the third one is a confocal. Now let's discuss each technique one by one and their efficiencies. So in this case, the optimum coupling efficiency is obtained by the positioning the fiber end very close to the laser facet, and this technique allows back reflections from the fiber to couple strongly into the laser, which produce noise at the device output that can cause performance degradations in high speed systems. So in the figure B, as we have seen, that is about the tapered hemispherical fiber coupling. So a simple and the popular technique is to employ a hemispherical lens formed on the end of the tapered optical fiber, and the third figure, that is a confocal lens system. So in this, the combination of the sphere lens of the green rod lens is common within such system because of the simplicity of the components. And third one is the coupling efficiency. So coupling efficiency of 40% we are getting with the sphere and the green rod lens system in a confocal design. So furthermore, the slight higher efficiencies have been achieved using the green rod lens with a one convex surface, that is of 49% of efficiency, and if we are using a silicon plano convex lens, we are getting an efficiency of 55%. So another technique to couple the power is the extended polymer tip technique. So more recently, a new technique has been developed in order to effectively couple the laser power into the standard single mode fiber without using lenses. So the technique involves fabricating a polymer tip on the end of the fiber, and a single polymer tip measuring between 15 to 150 micrometers in length may be viewed as an extension of the fiber core. So using this approach, a coupling efficiency up to 70% with 1.5 decibels coupling loss has been demonstrated. Moreover, it is also possible to produce the multi-peaked tips of a multi-mode fiber by applying the mechanical strain to the fiber during the tip growth process, where the multi-peaked tip essentially comprises a three-dimensional mold of the intensity distribution with the fiber. So let's discuss about the LED coupling to the fiber. So we are having the direct coupling to fiber, so also known as the butt coupling. So here we can see we are using a hemispherical ended fiber. So this is the fiber. Now the end of the fiber core is made up of the hemisphere, and we have the N electrode. Below this we are having the emitting area, through which we are having a window layer made up of N-type aluminium gallium arsenide. Then below this we are having an active layer which is emitting the photons, and these photons are entering the fiber core, as we can see in the figure. Next we are having the carrier confining layer. So carriers are confined within this stack, within this layer, and below this we are having the dielectric, that is of silicon dioxide SiO2, and below this we are having the p-type electrode made up of the plated gold heat sink and the gold silicate. Then BeO, and the last layer is made up of copper, that is for the metallization, where the dimensions are shown on the left, and the zinc diffused P layer is nothing but the carrier confining layer. So it consists of a planar surface emitting structure with a spherical ended fiber attached to the cap of epoxy resin. The geometry of this situation is such that it is essential that an active diameter of the device be substantially less than the fiber core diameter. So if increased coupling efficiency is to be obtained, in this case good performance was obtained with coupling efficiency around 6%. As we can see in the figure, we are having a lens coupling technique. In this we are using a truncated spherical lens. So this is the truncated spherical lens. In this truncated spherical lens, we are placing our fiber having the core and the cladding with a refractive index N1 and N2, as we have used these notations in our previous lecture as well. And this truncated spherical lens is nothing but a micro lens made up of Ti2O3 and silicon dioxide glass. And this is placed over a N-type indium phosphate substrate. Below this we are having a P-type indium phosphate and stacked with the P-type indium gallium arsenide phosphate. Below this we are having the N-type indium phosphate and the P contact is at the bottom. So active layer is between the P-type indium gallium arsenide phosphate, and we are using the heat for heat sink, we are using gold as a material. So the use of the truncated spherical micro lens for coupling the emission from an indium gallium arsenide phosphate surface emitting LED to the fiber. So let's discuss the lens coupling technique. So lens coupling technique employs a truncation, that is the spherical micro lens, as we have seen in the figure, and this configuration is shown in figure from an edged well of indium gallium arsenide phosphate or the indium phosphate with a double heterojunction, the surface emitting operating at a wavelength of 1.3 micrometers. So again, a requirement for efficient coupling is that the emission region diameter is much smaller than the core diameter of the fiber, and the overall power conversion efficiency, that is eta Cp, which is defined as a ratio of the optical power coupled into the fiber, that is Pc, to the electric power applied at the terminal of the device P, and is therefore given by, so coupling efficiency is given by eta Pc, that is the power coupled to the fiber and the power emitted from the source. So here we can use the edge emitting LED, that is ELED, and the lens is made up of the plano-convex lens. Here we have the plane surface and the wax surface, so we are calling it as a plano-convex, and this is the tapered arrangement. So we are having the lens ended fiber coupling. So this is the concept, that the photons are emitted or the light is emitted by the ELED and it enters the fiber. By using the plano-convex, we are coupling more power, more optical power to the fiber. Another technique is using the tapered green rod lens, and we are having a lens made up of the tapering, and the eLED again is used, and the power emitted from the source is coupled and it is focused at the fiber core. And if you are using a single mode fiber, then more power can be coupled using a tapered green rod lens. So the tapered fiber lens has been extensively used to couple power from eLED, that is the edge emitting LED, as we have discussed in the previous lecture as well, that is edge emitting LED, that is light emitting diode, into a single mode fiber. So the butt coupling of optical power from LEDs into the single mode fiber is substantially reduced in comparison with that obtained with a multi-mode fiber. So in this case, the tapered green rod lens was positioned between the high power eLED and the fiber. So let's discuss different techniques that is possible, that is with the help of the lens. So we are using the possible lensing schemes used to improve the optical source to fiber coupling efficiency. So first one is the rounded end. So if you are using a rounded end fiber, we can improve the coupling efficiency and more power from the LED can be coupled to the fiber. Another technique is using a small dia spherical lens known as the microsphere. So if you are using a microsphere lens, it can couple the power to the fiber. If you are using a large diasphere, it can also use to improve the coupling, and this is the imaging sphere, and the power from the LED will be coupled to the fiber. Another technique, we can use the cylindrical lens. Even the cylindrical lens can be the alternative, where the light can be concentrated at the focal point and we can improve the efficiency. Directly if you are placing the spherical ended, so here we can use the spherical ended of fiber and the spherical ended LED, means hemisphere is placed over the surface LED, and even the fiber is also rounded, that is a spherical ended. Similar to the laser technique, that is a taper ended fiber, here also we can use a taper ended fiber by tapering the core and the cladding, and the power and the coupling efficiency can be increased by using these techniques. So these are the examples of possible lensing schemes used to improve the optical source to fiber coupling efficiency. So theoretically, the coupling efficiency for surface emitting LED as a function of light emitting diameter. So if we increase the light emitting diameter, let's say we start from 0 and the diameter is increased by 10 micrometer with a step of 10 micrometer. So from 0 to 10 micrometer, the coupling efficiency is constant, that is 100%. So if edge diameter is in emitting area is increased again by 20, the coupling efficiency is decreasing. So after 10 micrometer increase in the diameter, the coupling efficiency is degrading or decreasing. So fiber with a numerical aperture of 0.2 and the core dia of 25 micrometer, this is the graph. So source to fiber power launching parameters. So a useful measure of the optical output of a luminescent source is its radiance. So at a given diode drive current, radiance is the optical power radiated into the unit, that is solid angle per unit emitting surface area, specified in watts per square centimeter per steradians, and the radiance of an optical source rather than the total output power is important parameter when considering the source to fiber coupling efficiencies. So main parameters are the type of the source, the type of the fiber used, the coupling technique used, the source structure, the diameter of the fiber, the source distribution pattern, the size of the emission area, and the acceptance angle. So these are the parameters we have to consider for defining the coupling or the power launching. So let's discuss the first parameter, that is the source output pattern. So to determine the optical power accepting capability of a fiber, the spatial radiation pattern of the source must be known. So the pattern shows the spherical coordinate system characterized by r, theta and phi, with a normal to the emitting surface being the polar axis. So surface LEDs are characterized by the Lambatian output pattern and the power delivered at an angle theta and measured the relative to the normal to the emitting surface and varies as cos of theta. So the emission pattern for the Lambatian source follow the relation. We are having the intensity distribution given by B, where that is theta is the azimuth angle and phi elevation, and we are having B naught cos of theta, where we can see that maximum distribution is at theta equals to 0, because cos 0 will be 1 and cos 90 will be 0. So at 90 degree we are having the minimum radiance. So B naught is the radiance along the normal to the radiating surface. So the figure shows the optical power radiated from a unit area of the source into the unit solid angle, that is watts per square centimeter per steradians. So here we can see the elevation angle theta, the azimuth angle shown in the xy plane. If we consider this as a x, y and z axis according to the rectangular coordinate system. So the radius at a point, at this point, the point of interest is r. So we can define in terms of r theta, r phi and theta, or r theta phi, whatever we are using. So the surface emitting LED has a Lambatian pattern as shown in the figure. We are having a Lambatian pattern that is defined as cos of theta. So this is nothing but a cos function, where we can see cos 0 is the maximum value, that is B naught. Here we are having the B naught, that is the maximum value, and it is decreasing and goes to 0 at 90 degree. So at 90 degree we are getting 0 value. So if this is the LED or the source, we can see the distribution. If it is the pencil beam distribution, then again the maximum will be at theta equals to 0. If you are using the another pattern that is known as the Lambatian pattern, so again it is going back to 0 at 90 degrees. So we can define the Lambatian pattern, that is nothing but B theta phi, that is equals to B naught cos of theta, and the radiance pattern for the Lambatian source and the lateral output of the highly directional laser diode. So both the source have the B naught normalized to unity. So if you consider the brightness of the source, that is also known as the radiance, the edge emitting LED and the laser diode have more complex emission pattern, and these devices have different radiance, that is B theta phi and B theta 90 in the planes parallel and normal respectively to the emitting junction plane of the device, and these radiance can be approximated by the general form, that is 1 by B theta phi, that is given by sin square phi by B naught cos of the transverse component represented by T and the lateral component represented by L. So these superscripts are to indicate this. So the integer T and L are the transfer and the lateral power distribution coefficient respectively. So in general, for edge emitting, L equals to 1, which is the Lambatian distribution with 120 degrees half power beam width, and T is the significantly larger. So for laser diode, L can take on the values over 100. So in this lecture, we have discussed about the optical source to the fiber coupling and the launching techniques. Then we have discussed the coupling or the launching technique, how we can couple it, and different examples we have used, that how we can use the lens based system for coupling the power from the LED to the fiber. Another is the parameter deciding the power launching or the coupling. And finally, we discussed the source output pattern with example. So there are two patterns we have seen. One is the Lambatian pattern and another one is the pencil beam pattern. So here we are going to stop this lecture. Thank you.